What if the biggest threat to your power, your GPS and your way of life, isn't coming from China or Russia but from 93 million miles away, and we only get 15 minutes warning? This is real, and most people have absolutely no idea. Think about everything running in your house right now. The router keeping you connected, the GPS in your truck, the ATM down the street, the hospital 2 miles away keeping someone's father alive on a ventilator. All of it depends on a power grid that can be taken down by the sun. And here's the part that should genuinely bother you. On December 24th, 2024, while you were wrapping presents or settling in for the game, NASA's Parker Solar Probe was flying directly through the sun's outer atmosphere at 430,000 miles per hour. The fastest human-made object ever built. Closer to the sun than anything in history. It went completely silent for 3 days. No signal, no confirmation, no way to know if it survived. The team that built it, the engineers, the scientists, the people who spent decades on this, could do nothing but wait. Because here's what they were chasing. Here's the question that sent a spacecraft into a star. Why does the sun randomly fire invisible storms of charged particles directly at Earth with almost no warning? And why can't we predict them? That question has been sitting unanswered since the 1940s. And the answer, it turns out, changes everything about how safe your world actually is. Here's where it gets weird. You'd think the closer you get to the sun, the hotter it gets. That's just common sense, right? Move toward the fire, you get burned. Back away, you cool down. The sun doesn't work that way. The surface of the sun, the part you can actually see, sits at around 10,000 degrees Fahrenheit. Hot, sure. But the corona, the sun's outer atmosphere, the region Parker was flying through, that reaches over 2 million degrees Fahrenheit. The atmosphere is 200 times hotter than the surface beneath it. That's like standing next to a campfire and finding out the air 6 feet above the flames is hotter than the coals. It makes no sense. It violates everything your gut tells you about how heat works. Scientists have known about this since the 1940s, and for over 80 years, nobody could explain it. But here's why you should care. The sun constantly blasts charged particles outward in what's called the solar wind. Think of it like a river of invisible electricity flowing through the entire solar system at over 1 million miles per hour. When that river hits Earth, it can fry satellites, knock out GPS systems, and collapse power grids. In 1989, a solar storm knocked out the entire power grid of Quebec, Canada. 9 million people lost electricity. In the middle of winter, a bigger storm today could cost the US economy over $2 trillion and leave parts of the country without power for months. We can't predict these storms well enough, not yet. And the reason we can't predict them is because we don't fully understand where they come from. That's what Parker was sent to figure out. In 1958, a physicist named Eugene Parker sat down and wrote a paper. He was a young professor at the University of Chicago, and his paper proposed something radical: that the sun was constantly exhaling a stream of charged particles outward into space. He called it the solar wind. The scientific community laughed at him. The reviewers who read his paper before publication called it, and I'm not exaggerating here, nonsense. They said it was physically impossible. The paper was rejected. Parker didn't back down. He pushed it through, and it eventually got published, largely because the editor of the journal respected him enough to give it a second look. 4 years later, NASA's Mariner 2 spacecraft flew past Venus and confirmed it. The solar wind was real. Eugene Parker had been right all along. He lived to see a spacecraft named after him. On August 12, 2018, at 77 years old, Eugene Parker stood at Cape Canaveral and watched the Parker Solar Probe launch into the sky on a mission built around his life's work. He passed away in 2022, but not before knowing that his idea, the one that was called nonsense, had become the foundation of an entirely new field of science. That spacecraft is still out there right now, doing exactly what he said was possible. So how do you build something that can fly through 2 million degree plasma and survive? This is the part that sounds impossible until someone explains it properly. The key insight is this: temperature and heat are not the same thing. I know that sounds like a riddle, so let me break it down. Temperature measures how fast individual particles are moving. Heat is how much energy actually gets transferred to an object. Out in the corona, the particles are moving incredibly fast, that's the high temperature. But there aren't very many of them. The corona is almost a vacuum. It's like the difference between a sauna and a blowtorch. A sauna might be 200 degrees, but you can sit in it for 20 minutes. A blowtorch is thousands of degrees, but the flame is so small and focused that it doesn't heat the whole room. The Corona is a very hot sauna with very few people in it. So the engineers at Johns Hopkins Applied Physics Laboratory built a heat shield, a carbon composite foam, sandwiched between two carbon panels, about 4.5 inches thick. On the sun-facing side, temperatures hit around 2,500 degrees Fahrenheit. On the other side, where the instruments live, room temperature. Here's the detail almost nobody thinks to ask about. The shield has to stay pointed at the sun with extraordinary precision. If it rotates even slightly off-angle, the instruments behind it get exposed, so the spacecraft has an autonomous system that constantly monitors its orientation and corrects itself without waiting for instructions from Earth. Because at that distance, a signal takes too long to travel. The spacecraft essentially has to think for itself. Parker didn't just fly straight at the sun. That's not how orbital mechanics work. Here's the counterintuitive part. To get closer to the sun, you actually have to slow down relative to it. And to slow down, Parker used Venus. 7 times. Over 6 years, Parker looped around Venus using the planet's gravity like a brake pedal, each pass pulling it into a tighter and tighter orbit around the sun. It's the same principle as a hammer thrower spinning in a circle before releasing, except in reverse. Instead of building speed outward, Parker was bleeding off speed inward. Along the way, something unexpected happened. In 2019, Parker discovered that the solar wind near the sun is full of these rapid, zigzagging reversals in the magnetic field. Scientists called them switchbacks. Nobody had predicted them. Nobody knew what caused them. Then in 2021, Parker crossed a threshold that no spacecraft had ever crossed before. It dipped inside the Alfvén surface, the boundary where the sun's atmosphere officially ends and interplanetary space begins. For the first time in history, a human-made object had touched the sun. NASA's own team compared it to visiting a planet for the first time. And that was just the beginning. December 24th, 2024. The final approach. The Parker Solar Probe went silent. That standard procedure, the spacecraft is so close to the sun that communication is impossible. The team at Johns Hopkins had no way to know what was happening. They had done everything they could. The math was right, the engineering was sound. But at 430,000 miles per hour, flying 3.8 million miles above the surface of a star, there is no rescue mission. There is no abort button. They waited. Christmas Day came and went. Then on December 27th, a signal arrived. Parker was alive. The images and data that came back were unlike anything scientists had seen before. Parker's camera, the Whisper instrument, captured the closest ever photographs of the sun's corona. And what they showed was not the smooth, steady atmosphere scientists had imagined. It was violent and chaotic and alive. They saw the heliospheric current sheet the boundary where the sun's magnetic field flips direction up close for the first time. Picture a massive, rippling sheet of electricity stretching across the solar system, and Parker flew right through it. They captured multiple coronal mass ejections, those massive eruptions of charged particles colliding with each other in real time. When two of these slam together, their paths become unpredictable. Their combined magnetic fields can accelerate particles to dangerous speeds. This is exactly the kind of event that threatens satellites and power grids, and now, for the first time, scientists could watch it happen up close. And those switchbacks, the zigzagging magnetic reversals discovered back in 2019? Parker's latest data is helping scientists trace them back to specific patches on the sun's surface where magnetic funnels form. The fast solar wind, it turns out, is partly powered by these switchbacks. A 50-year-old mystery is finally starting to crack open. The corona's impossible heat, still not fully solved, but Parker is giving scientists the data they need to close in on the answer. Let's be direct about what's at stake here. The 1989 Quebec blackout was a warning shot. The Carrington event of 1859, the largest solar storm ever recorded, happened before we had a power grid. If that same storm hit today, the damage estimates run into the tens of trillions of dollars globally. We are talking about a civilization-level disruption. Right now, our best warning time for a major solar storm is roughly 15 to 60 minutes. That's not enough time to protect satellites, reroute power grids, or warn astronauts. What Parker is building toward is a future where we can predict these storms days in advance. The same way we predict hurricanes. Not perfectly, but well enough to act. Every orbit Parker completes, every dataset it sends back, moves that prediction window forward. The slow solar wind, the switchbacks, the CME collisions, understanding these isn't academic. It's infrastructure, it's national security. It's the difference between a manageable disruption and a catastrophe. Here's what gets me about this whole story. Eugene Parker wrote his paper in 1958. The spacecraft named after him launched in 2018. It touched the sun in 2021. And it's still out there right now, flying closer and closer, sending back answers to questions that took 80 years to even ask properly. That's not a straight line. That's a human story full of rejection, patience, and the stubborn refusal to stop asking why. We built a machine that can think for itself, survive 2 million degree plasma, and fly faster than anything we've ever made, all to answer a question about why the sun's atmosphere breaks the rules. And the reason we did it isn't just to protect power grids, as important as that is. It's because we are the species that looks at a star 93 million miles away and says, I want to know what's happening in there. That instinct, that refusal to just accept the mystery, is the same thing that got us out of caves, across oceans, and eventually off this planet entirely. If you want to go deeper on how solar storms have already changed history, and how close we've come to a grid-down scenario more than once, that's exactly what we're covering next time. Hit subscribe so you don't miss it. And drop a comment below. Did you know Parker had already touched the sun back in 2021? Most people have no idea.